Everybody, welcome back to school. I hate recording myself, so I'm going to keep this brief. Um, so before the end of the world happened, uh, we were talking about quantum state vectors and how to describe the angular momentum of particles, specifically the spin angular momentum or intrinsic angular momentum that they have. And we created a mathematical model to be consistent with the sort of thought experiments and the results of the actual experiments that I shared with you. Um, and we came up with this kind of vector way of describing spins, um, but the states, the vectors themselves, don't point in a direction, but rather they represent sort of to what degree the particles are in a state of having angular momentum that points in a specific direction, which we talked about that before. Probably is still confusing, but we're gonna move on. So the very last thing we did was we introduced a third dimension. We started talking about the y-axis. So if we have particles spinning in an x, a y, and a z direction, the to represent all of those mathematically as distinguishable expressions, we kind of ran out of real numbers to use that had the properties that we needed them to have. Specifically, that we needed their magnitudes to the square of the magnitudes of two numbers to equal 1. So we briefly, towards the end, established that we could make everything work as long as we introduced the imaginary number I, and so now our vector space includes complex numbers. And it actually can get more involved than that. We can have states that are combinations or more complicated combinations of probability amplitudes of the z plus and z minus states, or x plus and x minus, or y plus and y minus states. So we need to go a little bit further into complex numbers, and so that's what we're going to do today. We're going to learn sort of more properties of complex numbers, but more importantly, we're going to learn new ways of representing and manipulating complex numbers that actually make the math easier, although it might look a little bit more complicated at first, but it really does make things easier in the end. Before we can do that, though, we have to go through a detour through Taylor expansions. So I will set things up for that now. First, we'll talk about what the Taylor series expansion is. So we've talked about it before. I've linked to a video from 3 blue, 1 brown, 3 brown, 1 blue. I don't remember. That does a much better job of explaining what a Taylor series expansion is and where this equation comes from. So if you don't remember, if you want to take a look, I encourage you. It's a really good explanation. But this is the equation. So we have the Taylor series expansion is equal to the function evaluated at the sort of central value a. A is arbitrary. We can choose it to be anything. Divided by 0 factorial times x to the 0th power, plus the first derivative evaluated at a, divided by 1 factorial times x minus a to the first power, plus the second derivative evaluated at a over 2 factorial times x minus a squared, and so on for increasing values of the factorial in the bottom, the number of derivatives you take, and the power of the x minus a term. Basically, all this means is that this first term represents the value of the function at a. The second term represents the slope. The third term represents the slope of the slope or the curvature, and etc. for all the others. And it turns out when you define all of these values for one single point, it gives you the entire function as long as the function is reasonably well behaved. So another way that we could represent the Taylor expansion is like this, which is just a simpler, cleaner form using summation notation, but we're not really going to use this. So we're actually going to deal with cases where we set a equal to 0. We're never going to choose a central value other than that. for our purposes, there won't be any reason to. So when you set a equal to 0, technically this is called a Maclaurin series, but it's just a special case of the Taylor series. It's just we're going to set a equal to 0 everywhere it shows up in our equation. This is just going to make our lives easier. So now what I'd like to do is let's actually do this for the function sine of x. Now the first thing we do then is we take the value, our function, and we evaluate it at our central value of 0. We divide by 0 factorial, which by the way is equal to 1. Don't worry about why, it just is. You can look it up if you want to know the mathematical reason for defining it that way. X minus 0, which is just x to the 0th power, is 1, so we're just going to ignore that. Now we add the first derivative term, which is going to give us a cosine of x evaluated at 0, divided by 1 factorial, times x minus 0 to the first power, which is just x. Now it's important to note that this notation, first of all, the apostrophe means first derivative, 2 apostrophes means second derivative, and so on. And it's important to note that we take the derivative first, and then we evaluate it at a. So we're taking the function sine of x. We take the derivative of sine of x, which is cosine of x, then we plug in the value of 0 into it. We don't say, okay, well, this is the cosine of a, or the sine of a, the first derivative of that is 0 because the sine of a is a constant. That would not be what we're looking for. Again, we take the derivative of the function itself first, and then we input the value of a, which is in our case 0. So next we add our second derivative term. Our second derivative term will give us a negative sine of x evaluated at 0 divided by 2 factorial times x squared. We can keep going. The next term will give us a negative cosine of 0. Right, the derivative of negative sine is negative cosine, and then we evaluate it at 0. And that's divided by 3 factorial to follow the pattern up top. And we can just keep on going. The next term, if we wanted to, would have a sine again, and it would have a 4 factorial in the denominator, and I realized I just forgot my x cubed, and so on. Now, right away, you might realize, well, we can just cross out all of these sine terms because the sine of 0 is 0. And so what that gives us is an expression for the sine of x, which is cosine of 0 divided by 1 factorial is 1, so this is simply x. The next term is 0. The next term is the negative cosine of 0, which is negative 1, so we have minus x cubed over 3 factorial. And if we continue the pattern, we would get plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial, and so on. With all the even terms are 0 because of these sine of 0 terms are going to just erase them, basically, leaving us with only the odd functions with alternating signs, because every 2 times we take a derivative, we introduce a negative sign. And so this is a way of representing the sine function. It's an infinite series of polynomials. And we can do exactly the same thing for the cosine function. So if we have cosine of x, our first term is going to be the function itself evaluated at 0 over 0 factorial times x to the 0. We leave it out. Then we can add to that the first derivative. The derivative of cosine is negative sine, so we have negative sine of x evaluated at 0 divided by 1 factorial times x. Then we add the second derivative term, which is going to give us a negative cosine of 0 divided by 2 factorial times x squared. The next one is going to give us a positive sine of x evaluated at 0 over 3 factorial times x cubed. And let's go one more time, and we get plus cosine evaluated at 0 over 4 factorial times x to the 4th plus all the rest of our infinite number of terms. And again, we can cross out all of the terms with sine of 0 in them, and we're left with the equation 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. Once again, alternating signs. Now, a couple things to note is the sine function is composed only of odd-valued terms. Well, that makes sense. The sine function itself is an odd-valued function. The cosine function, on the other hand, is even, or at least it is when it's just cosine of x. And so, unsurprisingly, it's actually composed of only even numbers. You also see here that when x is 0, the sine function immediately goes to 0. When x is 0 for cosine, it reduces to 1, and cosine of 0 is 1. So everything is working out quite nicely. Now, you might say, this seems pretty useless, right? Because who has time to add up an infinite number of polynomials? I mean, I don't even think YouTube could store that video if I tried to. So what is this useful for? One thing we can use it for is to compare functions, or even just to learn about the behavior of a function. For example, if the coefficients in our Taylor series expansion are all positive, or if they're all getting bigger and bigger, or if some of them are negative, it can give us an idea of how the function is changing, is whether or not it's increasing at an increasing rate or something like that. Especially if I have two functions and their coefficients are markedly different, maybe each coefficient gets bigger and bigger in one function and they get smaller and smaller in the second function, or they stay constant or something, then I can compare how these two functions are changing without actually plotting the whole exact function. Another way in which it can be really useful is if you only care about small values of x. If x is less than 1, then each successive term in the Taylor expansion becomes less and less important, right? Because you're raising it to a bigger and bigger power. So if x is, 0.1, then the term here is, there's a 0.1 here, there's a 0.01 here, a 0.001 here. So the power alone is decreasing the significance of each term by a factor of 10, by a whole order of magnitude. On top of that, if you look back over on this side, because the factorials are also growing, the successive terms are increasingly less important automatically, sort of by that metric already. So that combination of things tends to lead to the Taylor expansion converging to a result pretty quickly. And so what that means is eventually what you can do is you could cut off your expansion. You don't need to consider any terms after, for example, the squared term, because the cubed term might only change your answer by, 0.1%. The next term might only change your answer by 100%, or less even. And so this is a really useful tool. Oh God, I'm dying. Sorry. This is a really useful tool to analyze the behavior of functions around small deviations. If you go on to study physics or math or engineering, you will end up seeing quite a lot of this. It's pretty ubiquitous and it's extremely powerful. The third way in which Taylor series can be useful is because they actually allow us to generalize functions that we normally consider to be functions over real numbers, but now we can generalize them and figure out what would they mean if we put complex numbers into them. So for example, I know what the sine of function is. I know how to relate it to triangles. I know how to relate it to circles. But now there is this pesky little imaginary number in there, and I no longer have a clue what to do with this. I don't know what it means to have like a side length of a triangle to be I. I'm not sure if the same rules apply. But I do know how to plug the imaginary number I into this expression over here. I know that if x is equal to I, for example, let's say I want to just evaluate the sine of I. That should be a number. But what number? Well, I know that the sine of I is equal to the value, which is, in this case, x just becomes I, minus x cubed, so I cubed over 3 factorial, plus x to the 5, so I to the 5 over 5 factorial, minus I to the 7 over 7 factorial, etc. Now, obviously, we'd have to evaluate the series and figure out what does the actual final number come out to, and we'll learn some ways of doing that in a little bit. But suddenly I can put a number to this, right? I know what the number I is. It's just I. It's the square root of -1. I cubed is also the square root of, well, no, it's I times -1. I to the 5th and I to the 7th. I can evaluate those. My answer will be a complex number, but it will be a number instead of a question mark. And this brings us to your first homework assignment. So the first thing you're going to do is you're going to evaluate the Taylor expansion for the function e to the x. This should be even easier than for the trig functions because the derivatives of e to the x are nice and easy. And then once you've done that, you're going to use that and what we've already shown in this video so far to prove that the function e to the ix is equal to cosine of x plus I sine of x. This might seem a little bit bizarre, but you should be able to get there without a ton of work just by comparing your answer to question number 1 to the work we've already done so far. I recommend taking a break from the lesson for now, actually, and working these two questions out. I think the rest of the lesson will be more satisfying if you've already completed this part first. The questions are also included on the worksheet that's uploaded to the Google Classroom, so you can read them there as well. Whether you're moving on or whether you're coming back, let's talk about what some of the implications of this are. This expression is incredibly, maybe unexpected, but also incredibly powerful, and it leads to a lot of amazing results. There's so many cool things just mathematically and the way we use it in physics. So first of all, it's this idea that exponential functions are somehow related to trigonometric functions. We can even kind of invert this, and we can represent exponential functions without imaginary numbers to trig functions with imaginary numbers in different ways. We'll see some of that as well later. One of the first immediate things that shows up is the Euler identity. The Euler identity is what happens when we plug in pi for x. Well, I don't quite know what to make of e to the I pi, but I do know what cosine of pi is. Cosine of pi is -1. I also know what sine of pi is. Sine of pi is 0. Euler rearranged this just for the aesthetics of it and wrote it as e to the I pi plus 1 equals 0. I just realized I spelled identity wrong. So e to the I pi plus 1 equals 0. I mean, it just seems like a random collection of things, but some people have called it like the most beautiful equation in all of physics because it relates 4 of the most fundamental numbers that we deal with in mathematics. It relates e, which is a very special number. It relates the imaginary unit number I. It relates pi, another very special number, and 1, the multiplicative identity, and 0, the 0, the additive identity, the multiplicative 0, etc. And so this equation relates a lot of sort of major numbers in one little nice formula, and I mean, I think this is the part that none of us would really expect, but it turns out the number e to the I pi is nothing other than -1. So now let's look at this expression a little bit more closely. So if you think about it, right, x represents a real number. Cosine of x is a number between -1 and 1. Sine of x is a real number between -1 and 1. And so this expression looks a lot like a real number a plus I times a real number b. But this is just exactly how we've expressed complex numbers in the past. So e to the ix is actually a complex number different for every different value of x. And it goes a little bit farther because if you think about calculating the magnitude or size of a complex number, there are two ways of thinking about it. One way is we can take a squared plus b squared and take the square root, or we can write the magnitude, no, wrong color. Or we can write the magnitude as the square root of the number times its own complex conjugate. And either way, if we do that, we end up with the expression cosine squared of x plus sine squared of x under a square root. And we all know cosine squared plus sine squared is equal to 1. And so the magnitude of e to the ix is equal to 1. Sorry, let me erase this. The magnitude of e to the ix is equal to 1. So e to the ix is an imaginary number that has a magnitude of 1. In fact, maybe an even easier way to show that e to the ix is equal to 1 is to take the number e to the ix, multiply it by its complex conjugate, which is e to the I minus x, which when you multiply exponents together, you get e to the ix minus ix, which is e to the 0, which is 1. So lots of different ways to show the same thing, but this is really important. We have a way of representing lots of different complex numbers, all of whose magnitudes are equal to 1. Moreover, their magnitudes are equal to 1 in such a way that their real and imaginary components are represented by cosines and sine. Well, where else have we seen things with real and imaginary component, or with components represented by cosines and sine? Well, one is triangles. A right triangle with a hypotenuse of 1 has one side length that's equal to cosine of x, where x is the angle inscribed here, and the other leg of the triangle is sine of x. And so this is, we're relating these complex numbers to the components of a right triangle, or another way of thinking about this is as a vector with an x and a y component, or a real and an imaginary component. That leads us to the next thing. And somewhere else we've seen this exact same thing is in the unit circle. Only this time the axes are not the x and y axes, but they're the real number line and they're the imaginary number line. And so on the real number line, we have the numbers 1 and negative 1. But on the imaginary number line, our circle reaches I and negative I. And e to the ix, or e to the I theta, represents all the different numbers on this circle. So for example, if I wanted to pick out this point right here, I could actually represent it like this. I can take a line from the center of my circle. I can measure the angle from the positive real axis, and I can label that theta. Well, the length of this, if it's a unit circle, this is 1. And the complex number represented at this point on our complex number plane is the number z equals e to the I theta. It's important to note that we almost always consider this theta in radians. Otherwise, you have to do a conversion and deal with like pi over 180 degrees or something. In fact, we've already kind of seen this where just previously we saw that e to the I pi is equal to negative 1. So this point on our number line is simply equal to e to the I times pi. And conversely, 1 is equal to e to the I times 0, right? Which is just e to the 0, which is just 1, because the number to the 0th power is equal to the number 1. So we've already actually sort of started to see this already. But now we can get an idea. For example, we might expect that the number I to be equal to e to the I times, well, this is 90 degrees, or pi over 2 radians away from the positive real axis. And negative I is, by convention, we are always going to go in the clockwise direction, or almost always going to go in the clockwise direction. It just helps to avoid some potential inconsistencies. And so we would expect this to be, what is that? 3 pi over 2. E to the I times 3. I can't write. Hold on. We expect that to be e to the I times 3 pi over 2. And we could label any other point on this entire circle just by picking the appropriate angle in radians. And so now we've learned a way to represent all of the complex numbers with a magnitude of 1 in a really simple expression. It's just e to the ix, where x is an angle between 0 and 2 pi radians. So let's take a step back and let's talk about some quantum mechanics again. So let's consider that we have two state functions, psi1 and psi2. We're expressing them in terms of the z plus and minus basis with coefficients or probability amplitudes of a, b, and c, and this one should be a, d. And what we're going to do is we're going to take these two states and we're going to combine them and send them through a Stern-Gerlach device oriented in the z direction. Now, we don't know exactly what these states are because we don't know what the probability amplitudes are, but presumably the universe knows what these states are, right? Let's say these two states represent pieces of a probability wave that came through either a double slit experiment or a different Stern-Gerlach device or something, and now we're simply combining them back together. The universe knows what states they are, right? That's, what it means to be a thing in the universe. We don't know what it is, but this Stern-Gerlach device will output something depending on what these particular things are. And so let's say we run this experiment and we get a 0%, that I don't want that to be blue, a 0% chance that this is, oh, stop it, z plus, and a 100% chance that it's measured z minus. So we perform this experiment over and over and over and over again, and every single time we always find that the particle comes out here with angular momentum oriented in the z minus direction, never with spin up in the z direction. Now, to represent this mathematically, we can take these two states and we can combine them together. So what this is basically telling us is we want to do psi1 plus psi2. And for now, let's assume that psi1 and psi2 are each normalized themselves. So basically, psi1 represents what is the quantum state of a particle that would be measured here. So if I put a detector screen here, this tells me what the state of my particle would be, likewise here. And so these are normalized on their own. So when I combine them together, they won't be normalized anymore. So when I do that, I get a normalization factor times the original states just to make sure that the state I end up with right here, or rather right here, is in fact normalized on its own. So this would be psi2. Well, we know that there is a 100% chance that the particle will end up with spin in the z minus direction. So we know the probability is 1 that it will be in the z minus state. Well, if it has a probability of 1 in the z minus direction, which is our total wave function, then that implies that our probability amplitude is the square root of 1. Or rather, sorry, not the square root of 1. It implies that the magnitude squared of our probability amplitude is equal to, I need a new letter. So let's call this whole thing psi. And we know basically that psi has to be equal to, let's call it capital A for amplitude times z minus, with 0 amplitude in the z plus state. And this implies that the magnitude of A itself has to be equal to 1, or because A can be complex valued, we can't just say that A is equal to the square root of 1. And the reason why this makes a difference is because it implies that the square root of A with its own complex conjugate is equal to 1, which is a little bit more complicated. But if A is a complex number with a magnitude of 1, then that implies we can write A as e to the I theta. And therefore, we can write our quantum state as e to the I theta times z minus. I don't know what theta is. Theta is still a bit of a mystery. It's unknown. But I do know that this is the form that my wave function or my quantum state has to take. There can be no component, no amplitude in the z plus orientation, and there must be a magnitude, an amplitude with a magnitude of 1 in the z minus state. This actually gives us a little bit more information because if I think about psi 1 and psi 2, I know that when I combine them right here, their components in the z plus orientation have to cancel out, right? And if their components in the z plus orientation have to cancel out, that implies that A plus C has to be equal to 0. Or A has to be equal to negative C. But it doesn't really tell me what is the value of A or the value of C. It only tells me how they relate to each other. We've seen this before when we defined our states to begin with. And there, we just made arbitrary decisions. We said, I'm going to model a state in the z plus direction as, 1, 0, and so on. But here, we can't do that. We've already made that choice. We're already using our z basis over here. So we've made the choice about how we're representing our states. What this is telling us is that our experiment does not tell us the actual values of A and C. It only tells us how they relate to each other. It only tells us this information about their signs. We call this information about their signs, and it's actually more than that, right? For example, perhaps A is equal to 1/2. Well, if A is equal to 1/2, then C is equal to minus 1/2. Right? Maybe I've done another experiment and I've actually found that they have to have these magnitudes, right? I can do a different experiment that tells me that I can, for example, send this by itself through a z box, and that'll tell me the chance of finding z plus or z minus for just psi 1. And so I can work out what the magnitudes of A and C are through another experiment. So perhaps I've done that and I find that their magnitudes must be equal to 1/2. And so if A is 1/2, then C is minus 1/2. But maybe instead of A being 1/2, maybe A is equal to I over 2. Well, then C has to be equal to negative I over 2. Those are the two obvious ways I can get a magnitude of 1/2. But in fact, A could be equal to e to the I theta over 2. And therefore, C could be equal to negative e to the I theta over 2. And so we see that this information about the direction, if you will, of our state in the complex plane is unknown. I know that it has to have a magnitude of 1 over 2, but I don't know what direction it should point. So instead of being on our unit circle, it would be on a smaller circle with a radius of 1/2. Theta tells me which sort of orientation. Is it more real? Is it more complex? Is it somewhere in the middle? Is its real value positive, negative? Is its imaginary number positive, negative? I don't know. That is information I cannot discover from doing an experiment. And this information, this e to the I theta, that's right here, this information is referred to as the phase. The phase is its direction in the complex plane, independent of its magnitude, right? Because every number on this unit circle has the same magnitude of 1. But what we say is that each of these numbers have a different phase. Phase is a fancy word for angle. We use it in trig functions. We say the phase of a trig function, for example, would be cosine of x plus theta. This shifts our trig function by some amount depending on the phase that we add here. So this lets us sort of quantify an ambiguity that is fundamental to the nature of quantum mechanics. I want to emphasize there is not a single experiment we can do to measure in absolute terms the value of theta here. All we can do experimentally is determine what are the magnitudes of all of these different probability amplitudes and how do they relate to each other. I can tell, for example, if A and C are opposite each other, or even if they're out of phase by some small amount. Maybe in a different experiment, they don't find a complete destructive interference to get 0% here and 100% here. Maybe in a different experiment, I get 75% and 25%, or the other way around. Well, what that would imply is that the phase difference between A and C and B and D wouldn't be opposite in the case of A and C, or equal in the case of B and D, or at least additive in such a way. They'd have to actually be equal if A and C have equal magnitudes. So I could, for example, have, in a different scenario, I could have A be 1/2, and I could have C be, instead of negative e to the I theta, instead of negative 1/2, I could have A being 1/2 and C being I over 2. If C were I over 2 and A were 1/2, they would no longer completely destructively interfere, but they'd instead produce some different amplitude, which we would then have to normalize to find the resulting probability amplitude. But I think it's straightforward to see that if A is 1/2 and C is I over 2, these two numbers have a magnitude of 1/2 squared plus 1/2 squared, which gives us 1/2. So that would be at least the unnormalized combined amplitude. We'd then have to normalize it to figure out what the probabilities would actually be. But we can use this method of representing complex numbers to indicate how we don't know the actual phases. We only know that there has to be a negative sign right here. Without this negative sign, there's no destructive interference. With this negative sign, A and C cancel out. We're left with no Z plus term, only the Z minus term. With the negative sign, these go away. Again, if they're not completely opposites, if theta here is different from theta there, then they'll interfere in a more complicated way. Their real and imaginary components might not completely cancel out. They might not completely add up. Maybe the real components add and the imaginary components subtract, and we get more complicated interference behavior. So this is what we're leading to. This is why we're talking about all these different ways of representing complex numbers, because we want to get to a point where we can actually analyze that. Now let's talk about manipulating complex numbers and seeing what else we can do with complex numbers written in this new way. So the first thing I want to do, we've already touched on it already. I want to talk about how do I write an arbitrary complex number in this sense. We've already established that e to the I theta gives us a complex number somewhere on this unit circle in the complex plane. But what if I want a complex number that's somewhere outside of the unit circle with a magnitude greater than 1, or inside with a magnitude less than 1? Well, all I need to do is take any value on the circle and multiply it by some number, a real number. And so a complex number Z can be written as a real number times e to the I times another real number. Where R, I used R kind of an analogy to the fact that we're talking about a circle here. R can just be the radius of our circle. So we just take the unit circle and we blow it up to whatever size, we want it to be. Ooh, it's jumping. And we blow it up to whatever size we want it to be. So if I want a bigger number, I make a bigger circle. If I want a smaller number, I make a smaller circle. So this is a convenient way to represent any imaginary number, any complex number. A real number times e to the I theta will map out the entire complex plane. The farther from the origin I want to go, the farther from 0 I go, the bigger I should make this. And if I want to be entirely real, theta should be 0. If I want to be entirely imaginary, theta should be pi over 2, and so on, anything in between. So now that I have this, let's talk about what is negative z. Well, negative z is just equal to negative r e to the I theta. But that is a little bit, it seems cheap, right? What if I want to write this in terms of a new theta? What if I want this to be a positive? I want r to be a positive number. In fact, let's explicitly write that. I want this to be a positive real number. I want it to be like a radius. I don't really have negative radii. So I want to convert this. I want to convert this expression into something where this negative sign ends up in here. Well, the easiest way to do this is to look at our unit circle over here, or our circle. It doesn't have to be a unit circle. If I have a complex number over here, I think it's pretty clear that if I take its negative, I'm going to flip its real value from here to there, and I'm going to flip its imaginary value from here to there. That's directly across the circle. So the negative of a complex number is taking the number and basically adding pi radians, a rotation of 180 degrees, to the angle that we use to represent it. And so we can rewrite this as r times e to the I times theta, plus pi. Now, an alternative way of showing that this is true is I can always write negative z as negative 1 times r e to the I theta. But negative 1, we already established, can be written as e to the I pi. This goes back to the Euler identity, and that's right over there on my unit circle. And e to the I pi times r e to the I theta. I can combine the exponentials, and I get e to the, and I get r times e to the I pi, theta, plus pi. This right away is actually hinting at something to come later. I just talked about multiplying complex numbers. We're going to get back to a general way of thinking about multiplication related to this in a second. Before we do that, I want to talk about complex conjugates. Because it's easy to not confuse the two, but mistake the two. The complex conjugate is a little bit similar to this. There's still just a negative sign different, but it's important where that negative sign goes, right? So the complex conjugate of z is equal to r, which is a real number, so I don't have to do anything to it, times e to the minus I theta. So right over here, this is negative z. So where on my unit circle would z star be? Well, it's just I times the negative of the angle. So instead of measuring my angle from the x-axis upwards, I measure it from the x-axis downwards. And so this would be my complex conjugate. In other words, the complex conjugate represents a reflection over the real axis. Whereas the negation, simply taking the negative of my complex number, is a rotation of 180 degrees around the circle. So now let's go back and let's talk about multiplication in a little bit more detail. So let's consider two numbers, z1 and z2, both complex numbers with magnitudes or amplitudes r1 and r2, and phase angles, if you will, of theta 1 and theta 2 that tell us, which direction in our unit circle we're going. So let's consider how we would multiply these two things together. Well, this gives us z1 times z2 is equal to r1 times e to the I theta 1 times r2 times e to the I theta 2. Now, these are all just numbers. They might be complex numbers, but all the rules of multiplication still apply, and so I can multiply them in whatever order I want. So I'm going to group the real numbers out front, so r1 and r2, and I'm going to group the exponentials behind them. But again, when you multiply two exponentials together, you add their exponents. And instead of writing it like that, we can distribute the I, and we can write it as r1, r2 times I theta 1 plus theta 2. And again, if we think about this in terms of the unit circle, not the unit circle, just the complex circle, this number can be expressed, well, it has a radius of r1, r2, or a magnitude or an amplitude of r1 times r2, and it has an angle of theta 1 plus theta 2. So this is theta 1 plus theta 2. And so the multiplication of two complex number can be thought of as a scaling operation where their magnitudes are multiplied by each other. So if we have two very large valued or magnitude complex numbers, then they're going to result in a complex number with an even bigger magnitude. On the other hand, if one of them is very small, it might result in an even smaller amplitude than either one of them. And the other part of this operation can be thought of a rotation. If theta 1 were this angle, and theta 2 were this angle, then what we're doing is we're taking the complex number, maybe z1, and we're rotating it by an angle, theta 2, and we're scaling it by an amount, r2, right? This is simply r1, the magnitude of our original complex number, times r2, which gives us the new value of our thing, and then we rotate it by theta 2, starting from where it already was. So multiplication of complex numbers can be thought of this combination of two separate functions, and we can really visualize it quite nicely with this picture of a circle. Incidentally, division is also actually super nice. So, for example, I might consider a plus bi divided by c plus di, and I might tell you to rationalize this. Get rid of the I in the denominator. I don't like it. I want you to re-express this in terms of, G plus IF. But I don't know. What is G? What is F? That's a mess. I don't want to do that. It's a lot of work, and it's algebra, and I'm bad at algebra. On the other hand, if I want to know what is Z1 divided by Z2, well, Z1 is R1 e to the I theta 1, and Z2 is R2 e to the I theta 2. And R1 over R2 is just a number. I can do that. I can divide numbers by each other on a good day. And e to the I theta 1 divided by e to the I theta 2 can always be written like this, right? And so this is an interesting way of writing the complex conjugation of a number, right? If e to the I theta is a complex number, then the complex conjugate of it is e to the minus I theta, which can be thought of as 1 over our original number. And so this is just the idea of reciprocals. A complex number, a unit complex number, times its own complex conjugate gives us 1. That's a little diversion. But this we can easily express again because this is just this ratio of two numbers, but this just becomes e to the I theta 1 minus theta 2. So this is the same thing as multiplication. Again, we've scaled it. This time, instead of multiplying our original magnitude by the magnitude of the second complex number, we're dividing it. And instead of rotating it in the positive direction, we're rotating the direction of our vector in the negative direction, as seen by this negative sign. So this actually makes division, it doesn't make multiplication that much easier, but it can make it easier in some cases when I'm dealing with this a plus bi notation. There's less distribution that has to go on. But it dramatically simplifies the process of division. So the next thing we're going to do is I want to talk about if I have a complex number that looks like this, how do I get it to look like this? Or vice versa. We've seen a little bit of it before. You might already have an idea of how to do it, but let's go over it. To do this, we're going to make use of the relation from before, which is that I can write r e to the I times theta as r times cosine of theta plus I times the sine of theta, which I can write out as r times cosine of theta plus I times r times sine of theta. And here we can call this A, and we can call this B. So it's very easy, actually, to go from the exponential form to A plus BI. All I do is I take r times cosine of theta, and that's my real term, and I take r times sine of theta, and that's my imaginary term. And if I know what this angle is, I can compute what these are. So that's actually quite nice. So what if I want to go the reverse? If I want to go from A plus BI to this? Well, what I'm really doing here is I'm making use of the relationships between sine and cosine in the unit circle, or alternatively, just in a triangle. So if I have a triangle with hypotenuse r and a real component A and an imaginary component B, I should have color-coded this better with what I have over here, whatever. And I have an angle, theta, then I can use this to more easily go backwards, right? So this tells me that the magnitude of r, which is just its value, because r, again, is a positive real number, can be expressed as the square root of a squared plus b squared, right? It's just the hypotenuse of this right triangle over here. I should specify that it's a right triangle. Likewise, if I want to know the value of theta, well, again, it's a right triangle, and I know the two legs, and so I can write theta as the inverse tangent of b over a, right? The inverse tangent of the opposite leg over the adjacent leg. Now, there is one thing to be very careful of here. The inverse tangent of theta actually gives you two values because it's the ratio of sine over cosine, so you don't really know which one is negative and which one is positive if either one is the case. So you have to be a little bit careful. Because you could end up in the wrong quadrant. So if you were to just use a calculator and do this, for example, you might have the number z equals 2 minus I, right? Well, this number is not going to fall in a unit circle, so I maybe shouldn't have drawn it like this, but whatever. This number is going to fall in the somewhere 2, right? So 2 would be over here. Nope, wrong tool. 2 would be over here. And minus I would be over here. So this would be our number right here. But if you compute the inverse tangent, I actually don't remember which quadrant you could end up with if you make the mistake. It might be over here. I don't know, whatever. You can always test it out. But if you just read your calculator, you might end up in the wrong quadrant. And so you need to be a little bit careful. So you need to actually inspect the complex number you start out with to make sure that you've picked the right angle when you do this computation. So the very last thing we're going to do before I let you go is we're going to talk about how do I find the roots of complex numbers. For example, I know what the square root of 1 is. It's 1 and negative 1. I know what the square root of 4 is. It's 2 and negative 2. What is the square root of I? It's a good question. What's the square root of, 2 minus 3i? Or what's the cube root of 1, right? It seems like a really simple question on its face. The cube root of 1 is easy. I know that 1 cubed is equal to 1. But if it's a cube root, then there should be 3 of these roots. And I have no idea what the others are. You might test -1, but -1 times -1 times -1 is -1. And so that one does not work. And so we have to figure out what the rest of the 2 roots are. And so the way that we do it is, if it's not 1 and it's not -1, and it's certainly not any number but any real number besides those 2, then the only thing left is it's a complex number. And so the way that we find this out is, let's say some complex number is e cubed is equal to 1. Well, I can write z as r e to the I theta, and that's equal to 1. And I can do this exponentiation out, and I get r cubed times e to the I theta cubed. But when I cube an exponent like this, I can write it as e to the I times 3 theta. And that has to be equal to 1. Well, we know right away that this part right here has a magnitude of 1. And that implies that this part right here has to be equal to 1. Because if this is not equal to 1, and this has a magnitude of 1, there's no way I'm going to end up with a number 1. So r cubed has to have a magnitude of 1, and so we're just going to get rid of it. We're just going to get rid of it. And so we're left with e to the I times 3 theta has to be equal to 1. But that still feels like I'm stuck because I don't know how to do that. And the way I'm going to get around that is, again, I'm going to make use of my unit circle. Drawing circles is hard, but I can do it. And I know that the number 1 on my unit circle is represented by an angle of 0 degrees. Well, if I write e to the I times 0, I'm just back at square 1 because 3 times theta, if I want 3 times theta to be equal to 0, then theta has to be 0, and that's not really ideal. But the thing is, I also know that e to the I times 2 pi is equal to 1. So e to the I times 0 is equal to the e to the I times 2 pi. And in fact, it's also equal to e to the I times 4 pi. And it's equal to e to the I times 6 pi. And e to the I times 8 pi, and so on. Every time I go around the circle one full time, I end up back where I started. So this is how I'm going to actually compute my roots. So let's pick one of these values. We already did this one. This gives me that one of the cube roots, e to the I times 3 theta 1 is equal to the e to the I times 0, and that implies 3 theta 1 equals 0, that implies theta 1 equals 0, and that implies that z is equal to e to the I times 0, which is simply equal to 1 by the normal rules of algebra that we learned a long time ago. But let's try a different one. What if I say e to the I times 3 theta 1 is equal to e to the I times 2 pi? Well, again, the only way for these two things to be equal is for their exponents to match. And so 3 theta 1 has to be equal to 2 pi. And so I get 3 theta 1 equals 2 pi. And so theta 1 is equal to 2 pi over 3. And that tells me that my second root is equal to e to the I times 2/3 pi. I want to emphasize that I no longer have an r here or here, because over here we established that it has to be 1 in order for this to have a chance of working. And so we still only have 2 roots, so let's try this again. E to the I times 3 theta 3 is equal to e to the I times the next way of expressing the number 1, which is e to the I times 4 pi. I've now gone around my circle once and then twice. And this gives me 3 theta 3 is equal to 4 pi. And this gives me that theta 3 is equal to 4 pi over 3. And this implies that my third root is equal to e to the I times 4 pi over 3. Now, you might ask, why can't I keep going? Over up here, right, I didn't stop at 4 pi. I went to 6 pi and 8 pi. These are all ways of expressing the number 1. So if I try to do this one more time, I can say that e to the I times 3 theta 4 is equal to e to the I times 6 pi. This gives me that 3 theta 4 is equal to 6 pi, and that theta 4 is equal to 2 pi. But this gives me that z4, my fourth cube root, would be equal to e to the I times 2 pi. But this is just the number 1. We already found the number 1. That was our very first root over here. And so this one is not a new root. It's just double counting a root that we already found. So you could keep doing this forever, right? You're never going to run out of ways of going, like more ways of going around the circle a complete time. But if you keep doing it over and over again, all you're doing is you're re-expressing the roots that you already found. If I did it for 8 pi instead of 6 pi, I would get 8 over 3. But 8 over 3 pi is going to be the exact same thing as this, because, again, if I draw my unit circle, let's make a nice circle this time. Then 2/3 pi is 120 degrees. And so let's use a different color. So 2/3 pi is 120 degrees, which is a little bit more times than 90 degrees. So this is z2. Well, 8/3 pi is just 2 pi plus 2/3 pi. And that would give us 2 pi plus 2/3 pi, which is just z2 again. And so it gives us the same point on our complex plane, and so it actually means the same number, even though we're expressing it with a different angle. This is the redundancy of polar coordinates, right? The same point can be expressed in an infinite number of ways, because I can just keep going around and around the circle. This really is just polar coordinates, except instead of an x and a y-axis, I have a real and an imaginary axis. Now, if I draw the rest of these out on the unit circle, well, z1 is just this number. And then z3 is 4/3 pi, which is 1 pi, which is 180 degrees, plus another third pi, which is 60 degrees. And that gives us 240 degrees. And that's z3. And you'll notice that the angle between each of these is 2 pi over 3. Or 120 degrees. And so the roots of the 3 cube roots of the number 1 are equally spaced around the circle in our complex plane. And that's actually a general feature of roots of complex numbers, they tend to be equally spaced out. I'm hesitant to say they're always equally spaced out now that I'm saying it, but any root of the number 1 is definitely going to result in this kind of pattern. Weirder complex numbers might not work out so cleanly. We'll have to think about that. So this is the basis for the homework that's posted on the Google Classroom. I'd like you to complete the homework by Tuesday night, or read the instructions on the Google Classroom. And if you have any questions, you're free to ask for help on the Discord from your fellow students or from me. You'll also be receiving a schedule of when my office hours will be held through Zoom. See further instructions for that on the Google Classroom. Bye, everybody.